Okay? Next. So LRU is considered a good replacement policy and is often used. So the problem is how exactly to implement it. So there are two simple approaches commonly used, right? So you've got the counter implementation and you've got the stack implementation. So for counter, every memory access increments a counter. And the current value of this counter is stored in the page table entry for that page. Then finding the LRU page involves simple searching the table for the page with the smallest counter value. So note that overflowing of the counter must be considered. Okay? Now for the stack implementation, another approach is to use this stack implementation, and whenever a page is accessed, pull that page from the middle of the stack and place it on the top. Right? So the LRU page will always be at the bottom of the stack. So because this requires removing objects from the middle of the stack, a doubly linked or double linked list is the recommended data structure. Okay? So note that both implementation of LRU require hardware support, either for incrementing the counter or for managing the stack. Counter for the counter implementation and stack for the stack implementation. Okay? As these operations must be performed for every memory access. Okay? Now, neither LRU or OPT, okay, exhibit Bellad's anomaly. Both belong to a class of page replacement algorithms called stack algorithms, okay, which never suffer from Bellad's anomaly. So a stack algorithm is one in which the pages kept in memory for frame set of size n will always be a subset of pages kept in the frame size of n plus 1. Okay? So in the case of LRU, and particularly the stack implementation thereof, the top n pages of the stack will be the same for all the frame set sizes of n or anything larger. Okay? So next is the LRU approximation algorithm. So unfortunately, full implementation of LRU requires hardware support, and few systems provide the full hardware support necessary. Okay, so however, many systems offer some degree of hardware support enough to approximate LRU fairly well. In the absence of any support or hardware support, PIFO might be the best available choice. Okay, so in particular, many systems provide reference bit. All right, so reference bit for every entry in a page table, so which is set anytime that the page is accessed. So initially, all bits are set to 0. Okay, all bits are set to 0, and they can also all be cleared at any time. So 1 bit of precision is enough to distinguish pages that have been accessed since the last clear from those that have not. Okay, but does not provide any finer grain of detail. Okay, next. So next LRU approximation algorithm is the second chance algorithm. Okay, so generally it is a first in first out, except the reference bit is used to give pages a second chance at staying in the page table. Okay, so when the page must be replaced, the page table is scanned in first out, circular queue manner. So if a page is found with its reference bit not set, then the page is selected as the next victim. Okay? So if, however, the next page in the PIFO does not have its reference bit set, then it is given a second chance. So that's why it's called the second chance algorithm. Okay? So the reference bit is cleared and the PIFO search continues. If some other page is found that did not have its reference bit set, then that page will be selected as a victim. And this page, okay, so the one being given the second chance will be allowed to stay in the page table. All right. So if, however, there are no other pages that do not have their reference bit set, then this page will be selected as the victim when the PIFO search circles back around to this page on the second pass. All right. So that's the consideration for the second chance algorithm implementation. Okay. Now, if all reference bits in the table are set, then second chance degrades to first in, first out. So as always, our fallback is always the first in, first out, but also requires a complete search of the table for every page replacement. Okay, so as long as there are some pages whose reference bits are not set, then any page referenced frequently enough gets to stay in the page table indefinitely. Okay, so this algorithm is also known as the clock algorithm. So other term is clock algorithm, from the hands of the clock moving around the circular view. So this is in clockwise movement. Okay. Next, so another consideration would be the enhanced second chance algorithm. Okay, so what do we have with the enhanced second chance algorithm? So the enhanced second chance algorithm looks at the reference bit and the modify bit. So still remember the dirty bit we're talking about earlier? So that is that will serve as a reference as an ordered page and classifies pages into 1 or 4 classes here. So 00, neither recently used nor modified. 01, not recently used but modified. Okay. 10, recently used but clean. All right. And 11, recently used and modified. So this algorithm searches the table or the page table in a circular fashion in as many as 4 passes. Okay, so looking for the first page it can find in the lowest numbered category. So example, it takes a pass looking at 00 and then it can find 1. It makes another pass looking for 01, etc. Okay, so the main difference between this algorithm and the previous one is the preference of replacing a clean pages if possible. All right. Okay. So next would be counting algorithms. Okay. So there are several algorithms based on counting the number of references that have been made to a given page, such as the LFU, least frequently used, okay, and then you've got most frequently used, MFU. Okay, so what we have on the first on part of our demo was LRU. So this one is LFU. Okay, so replace page with the smallest count. That's LRU. Replace the page with the lowest reference count. Okay, so a problem can occur if a page is used frequently initially and then not used anymore. So as the reference count remains high, okay, so a solution to this problem is to right shift the counters periodically, yielding a time decaying average reference count, because we need to replace page with the smallest count here. Okay, so the next one would be the most frequently used algorithm. Okay, so replace the page with the highest reference count. So the logic behind this idea is that pages that have already been referenced a lot have been in the system a long time, and we are probably done with them. Whereas pages referenced only a few times have only recently been loaded and we still need them. Okay, so in general, counting based algorithms are not commonly used. That's why we did not include it on the examples we provided. Okay, so we already have we only provide examples on the first in first out. Okay, so least recently used and optimal. Okay. All right. So next is the page buffering algorithms. So what is a page buffering algorithm? So there are a number of page buffering algorithms that can be used in conjunction with aforementioned algorithms. So to improve overall performance and sometimes make up the inherent weakness in the hardware and or underlying page replacement algorithm. Okay? So maintain a certain minimum number of free frames at all times. When a page fault occurs, go ahead and allocate one of them free frames from the free list. Okay? To get the requesting process up and running again as quickly as possible. And then select a victim to write to disk and free up a frame as a second step. Okay, so keep the list of modified pages, and when the I/O system is otherwise idle, have it write these pages out to disk. And then clear the modified bits, thereby increasing the chance of finding a clean page for the next potential victim. Okay? Next, so keep a pool of free frames, but remember that what page was in it before it was made free. So since data in the page is not actually cleared out when the page is freed, it can be made an active page again. So without having to load in any new data from disk. So this is useful when an algorithm mistakenly replaces a page that was in fact needed again soon. All right? So that's the page buffering algorithm.